briefly, what I do at SSU, I lead a group of experimental physical and materials chemistry, and most of our work is focused on studying diverse electrochemical processes in chemistry, or rather at the interface of chemistry and biology, which have quite a bit of implications in energy harvest and generation, catalysis, sensing, and actuation. So today's lecture, of course, I'll be talking on energy, which is, I think, as important as clean water or environment to mankind. And the talk will be basically focused on renewable energy sources, where or in fact, when we talk of energy, you basically have two arms of the energy. One, of course, you have to generate it by any way, which most of the in recent times, or which is due to fossil fuels, but we are actually moving away from fossil fuels to renewable sources like solar and wind and water and so on. But the other, of course, which is not much talked about, is how to store it efficiently. Just to kind of give you some idea about where storage would be very interesting and very useful, would be if you look at a grid, an electric grid, where of course it is producing power usually using the conventional means, but it also has a renewable form of energy being fed into the grid. So if you are sometime in the early hours of the day, you have this excess power, which is basically the base load plus the energy that is generated from the renewable source, which could be solar or wind or anything. If you don't have any storage, then this actually just goes waste. So if you have a storage, a component integrated with the grid, this can be sent to storage. And at peak hours, you can actually take in from the storage and meet the demands during the daytime. So a strategy like this, there are plenty of advantages. Of course, you tend to, of course, prevent misuse. You can prevent wastage and optimally manage your resources, and of course, you can protect the environment, because grids are in top of the line, top of the list in generating greenhouse gases. All right, so how can you store? Of course, there are four principal ways of storing energy. Of course, there are mechanical, electrical, chemical, and electrochemical. Of course, the last two, they're not much of a demarcation, but we can still kind of separate them into two different categories. So the mechanical storage, of course, the bulk of it all over the world is due to the pump hydroelectric, hydroelectricity. Then if you have compressed air storage energy systems, flywheels, and so on. And what I've given here and below are the quantum of energy that these kind of that this type of storage can produce for you or store for you, going from megawatt, the process rate going from minute to hours, cycle life of 10 to 25 years, a relatively high efficiency of 90%. And then, of course, you have the superconducting magnets, which are also equally good, but very expensive. A chemical storage in the form of hydrogen. But the problem is we really don't per se handle hydrogen. It is stored in some form or the other, and that brings down the equivalent energy of hydrogen storage. And then finally, are the electrochemical storage systems, like batteries and supercapacitors. Of course, you have fuel cells and so on, but they're not really classified as a storage system, more of a generation system, because you continuously feed in fuel in the form of hydrogen, and you produce energy. So among this, the electrochemical energy sources are, of course, becoming very important, because they're clean, and in terms of very large applications like grids or electric vehicles and so on, they have a fairly high turnaround efficiency. They're compact. You can scale it up, scale it down, and among them, of course, batteries are a very important component, because they're pretty high energy systems where you can store a lot of energy in a very small area, or you can scale it up and so on. So I'll be actually so when I mention batteries here, these are reversible electrochemical reaction where you have a reversible or a rechargeable battery system where an electrochemical reaction is going in both directions. All right, so just what we actually look in a battery typically is, and I'm actually giving a typical physical chemist perspective, and not to annoy the chemists in the crowd who are classified as chemists or organic chemists. So the first point that we look at is the amount of energy that the reaction can give you, which is given in watt-hour per kilogram. And how do we get it? This is very straightforward, following from Faraday's laws of electrolysis. And we have a open circuit voltage, which is coming from the electrochemical series of elements. And then you multiply this by the capacity, where you have the number of reversible exchange of electrons times the Faraday divided by the atomic or the molecular weight of the system. So if you go just by this prescription, we would be typically happy on the left-hand side of the periodic table, getting lighter elements, which is going to boost up the energy significantly. But if you want to use elements on the right-hand side, it should be, a multi-electron process. Typically, on the left-hand side, we have less than one or one electron process the system. So these are some of the parameters that one plays with. Apart from this, one also looks at the method of storage. So you can look at intercalation chemistry, where your dominant ion will be going in and out of a solid state material, very fixed amount, which is controlled by the space inside the crystal structure of the system. Or you can, for example, use a conversion chemistry where you form a compound or through formation of compound or in the both directions. All right, so the other important thing is, of course, the efficiency of the process. At what rate you can charge-discharge the system. So this depends typically on the charge transport. So here two parameters are important. You have the electrolyte conductivity, which is the ion conductivity of the system in the bulk, as well as how it gets through or transports across the interface with the electrode. And then, of course, you have the electrode characteristics, which controls the ion diffusion coefficient. So this parameter will tell you how quickly you can charge-discharge a battery. So these are the two important characteristics or parameters one keeps in mind in almost everything, starting from materials design to the ultimate stack level assembly of a battery. Okay, so we've been knowing batteries for a very long time. The very first battery is, of course, designed by Volta from voltaic pile, or if one wants to go even further up, Franklin, of course, he termed the coin of battery. But since about 1800, it has evolved in various different ways, in chemistry, in terms of power output and so on, right up to the present day, where you have a large number of different elements participating in the chemistry. Of course, this is for battery. Of course, you have other electrochemical systems which has a different timeline. I'm not going to go into that. But if you just stick to batteries, I believe many important chemistries came up. I believe lead-acid battery is now kind of saturated. It is running many of our systems, but with very limited effect. I believe people started really think big with batteries around 1990s when the lithium-ion battery came into being. The commercial product was brought out by Sony, but the timeline in terms of research, there are many contributors. Of course, John Goodenough is considered to be the inventor in terms of, at least at the lab level. Since its inception, I believe until now, the kind of applications where lithium ion has gone into, it is kind of accepted as a kind of a gold standard in battery, because the amount of energy that can be withdrawn from this kind of a system is completely unmatched. So I'll quickly go into what how the lithium-ion battery works. In a lithium-ion battery, there is no lithium metal. We use lithium compounds, which stores the lithium ions by various mechanisms. the most widely used is intercalation chemistry, where you have this kind of a layered system, and depending on the direction of the current, the lithium ions will rock back and forth through the solution, and this is how you gain energy. So this is shown for a particular compound of lithium transition metal oxide, which is a layered system, or a manganese oxide, with a lithiated graphite, which is again a layered system. So this gives you some reasonable amount of energy. This is, of course, the practical energy. The theoretical energy is much higher. And this is how it stores energy. So with this very limited amount of lithium ions that you can store, which is typically less than 1 electron reversible process, you already have a gain of an order compared to the age-old lead-acid batteries or the nickel metal hydride systems, which actually have gone out of market because of the toxicity of various elements used in the battery. So you have this kind of a gain if you actually go to a very lighter element, such as lithium. So what this has given us is, starting from very early phones, mobile phones to smart phones, and then of course some power tools. So what we would like to now do is to go the other way, where we want to use the same chemistry to run bigger systems right up to an electric vehicle or an electric grid. So using the same chemistry, people have gone into materials exploration, looking at higher operational voltage systems. And they've built this kind of a Ragon plot where, starting from carbon, people have moved to alloying systems, conversion systems, and they've used even higher voltages with respect to by varying the transition metal composition in the solid state compound. So the important thing that has to be kept in mind is the homo-lumo gap of the electrode should be in between the degradation voltage of the electrolyte. So this has been one way of increasing the performance of the system. Of course, this is some contribution we had this year, where we have a layered system which shows a mixture of both insertion and alloying chemistry in one compound. There have been ways of improving the architectures that typically controlling the manipulation of the charge transport at small length scales, using graphene, specially architectured graphene, where you have transport even in the third direction. In addition to the two-dimensional transport, you have special architecture in the form of alloys being put inside a carbon fiber, or using very advanced techniques to grow thin films, where you're trying to manipulate the transfer through a network of nanovolts. Apart from this, of course, the electrolyte is very important, and this is also where we've contributed over the last several years, looking at systems moving away from liquid to solid-like systems in the form of gels or structured hybrid liquid electrolytes, which all give very interesting properties and improve the battery system. But there's actually a limitation to all that we are doing here, and in fact others also do, is the extension of functionality, because we are trying to kind of scale it up to a bigger system, and cost could be an important criteria. And that's essentially because we are looking at applications where it's not just a single entity, but you're looking at a full city having running on electric vehicles or a power grid supplying to a city or a state. So what could be the alternatives? So one would be, you can go beyond lithium ion and explore other metal ion systems like sodium-based systems, or magnesium or calcium or aluminum, which are earth abundant and cheaper. But the problem here is, you're actually going to fairly non-trivial chemistry or electrochemistry of these systems. And you always tend to land up with lower performance, because compared to lithium, these are much lower in voltage when you put them, so you get a much lower capacity. The other would be to look at, if you really want to go beyond lithium, go from compound-based electrodic systems to element-based systems. The idea is, to again kind of exploit multi-electron processes, which is missing in some of the lithium-ion systems or sodium-ion systems. So you can have a whole range of chemical couples, but not all of them won't be useful, though you can publish papers. But things like lithium fluoride, which gives you massive energy, you cannot use them to make a practical battery. What would be interesting to look at certain couples where you have oxygen or where you have sulfur, because the energies are very high and they're pretty cheap. Things like oxygen or nitrogen, they're free to us. You can actually use the atmospheric nitrogen or oxygen to run the battery. So this is actually giving you a rough chart. If you open a Sigma Aldrich website, you will see these are fairly expensive systems, so you want to replace them by cheaper or even free cathode systems into a battery. So typically, what is a metal air battery? I'm just showing here, you're actually using the oxygen directly from the atmosphere, and this undergoes a redox reaction, and this way we actually store the energy in a reversible manner. It gives you very high energy storage with lithium or sodium or zinc and magnesium and so on. So in sulfur, what we do is we replace oxygen, and you have actually a sulfur as a cathode. The sulfur being non-conducting both electronically and ionically, you need to store this in some scaffold. But the problems with sulfur chemistry is, you charge-discharge a battery, it goes through these large number of these various polysulfides. Some of them are actually soluble in the liquid solutions that are used as electrolyte in the system. So the problems are, again, plenty. It's a tackleable problem. So you could have anode poisoning, the sulfur, the final product forming on the anode side rather than on the cathode side. You could have volume expansion, and then of course you have to handle the insulators, the insulating nature of sulfur and the polysulfides which are formed during the charge and discharge. So one of the essential ideas here is to design efficient scaffolds which can give you high sulfur loading and efficient encapsulants. So I think over the last 3-4 years, we have worked extensively on various sulfur systems, metal sulfur systems, especially lithium, sodium, and magnesium. These are some of the examples where we're typically looking at, increasing the sulfur content and, localizing it in a very deterministic manner as to where the sulfur is in the host. What we found out in all our studies, there are 4 critical points. One, of course, is the structure is very crucial in loading. Then, of course, how the sulfur is, because there's a lot of confinement effects in the pores of the encapsulant. And then, of course, using a lot of in operando experiments, spectroscopy, microscopy, both at the lab and at the synchrotron level, what we observe is the incompleteness of the reaction and so on. So that leads to lower capacity. Of course, we have moved on. We moved, instead of going up, we have moved down to selenium, tellurium. Advantages are that, you're dealing with electrode conductivity, easier manipulation of polychalcogenides, but you have lower specific capacities. You can also build sulfur with other metals, but then, as I said, the electrochemistry becomes quite demanding, and you have other challenges with respect to the physical properties of the ion motion and confinement effects and so on. I'm trying to conclude. So this is actually where we are presently due to lithium ion. We have improved quite a bit from 1991, and we're looking at more applications. We would like to actually very soon reach here with some other metal, maybe sodium, such that we can have advanced portable devices, electric mobility. But the final goal will be to to attack the ICE, the combustion engine, and build autonomous energy supply systems and so on. So these are some of the criteria which we would like to has to be followed in order to replace a gasoline with an electric mobility, and of course integration of EChem storage with the grid and renewables. And I believe the most important thing is there should be no mental block. There's a lot of mental block in adopting these the newer forms of energy and the device and so on. So thank you very much.